All right, so let us begin. Last class we talked about estimating the error, right? So before that we talked about the approximation methods in number system at floating point, fixed point. We talk about rounding and chopping, right? So based on that we see that there will be a difference between the real solution or real value and the approximated value because of these rounding and choppings on floating point and fixed point numbers as well. So based on that, we talk about types of errors, right? Absolute error and relative error. So today we are going to see an estimation for those errors, right? In terms of some known values, right? So we call it error bounds. So this is called error bound. This section, right? So let's say right? So let us say alpha be a given real number, right? And okay, so let us say alpha be a real number and FL of alpha be a floating point representation of alpha, right? In obviously you know in FL of BT. Right, so then okay, so now because we set alpha f of alpha is the floating point representation of a real number alpha, so you know according to what we studied, the FL can be chosen by chopping or rounding in FL of BT. Right, so we can do both chopping and or rounding, either chopping or rounding in the floating point system. So if we apply chopping, then the relative error is bounded above by b to the power 1 minus t. And if the FL of x is obtained by rounding in FL of BT, then the relative error alpha minus F alpha over no absolute value of alpha is bounded by half of b to the power 1 minus t. So we can prove both the results, right? So if the value is obtained by chopping, then we say it is that bounded by that first value, and if it is by rounding, then the value is bounded by the second value. So we will prove one by one. So if alpha is given, then you can write alpha in the standard scientific notation, that is a fraction times exponent. Right. Never mind. We'll stick to the plus. Okay. So if alpha is a real number, then you can write it in the standard notation, right? So suppose it has n digits in it, then you can write it as 0.d1, d2, d3 up to dn times b to the power e. Any real number you can write it in this form, right? So it can have any number of digits, right? So that is fine. But right, so you know that if you are chopping, right, FL of BT, so you cut down all the digits after this point, right? So you cut down all the digits after this point, right? So in that case, you can say that your FL of alpha is this. This is going to be your FL of alpha if FL of alpha is obtained by chopping. So clearly you can write alpha minus FL of alpha absolute value. Okay, so if you subtract f of alpha from alpha, right? And then say for example, even if you put plus or minus, it doesn't matter, right? So you just subtract. So on the first t digits, the digits are same in FL of alpha and alpha. So when you subtract, they are all gone. So you ended up with this, right? So this you can write it as follows. Right, so if you move the decimal, right, the dot t places back, you will get 0.dt1 t plus 1 up to dn times b to the power e, and then there is an e to b to the power minus t there. So if you combine all of them, you get this. Also, because it is a base b term, right? You know that the first digit is between 1 and b. If it is 0, you move one more step back and you can write it as b to the power e minus t, right? So t minus 1. So that's not a big deal. So if you write it, you know that the t plus 1 should satisfy this condition, right? So because that is how you know we write the numbers in base b. Okay. So now what you are going to do is you are going to verify certain things, right? Okay, so right. Okay. Now notice that this is clear because this is a fractional part, no integers there, 0 point something. So that is a fraction. So that fraction is always less than 1, right? So you know that 0 point dt plus 1 up to dtn is strictly less than 1. So you know that, right? This is alpha times alpha minus f of alpha, FL of alpha is less than 1 times b to the power e minus t, right? So that is one thing. Now x, right? So let me name this as equation 1, okay? Okay, so now absolute value of alpha is 0 point d1 d2 up to dn times b to the power e. But again, you know that the first digit is between 1 and b, right? Equal, greater or equal to 1, less than b. At the same time, right, the next digit are 0, 1 up to b. So you put the smallest possible values there. So you get 0 point, that number is larger than 0 0.1000 b to the power e. So if you write that in a polynomial notation, you get b to the power minus 1, and then there is a b to the power e. So you get absolute value of alpha is greater than or equal to b to the power e minus 1, right? So this implies 1 upon absolute value of alpha is less than 1 upon b to the power e minus 1. Let me name this as equation number 2. Right? So here 1 upon absolute value of alpha is less than or equal to, I have to say equal to 1 upon b to the power e minus 1. Right? But in equation 1, you have absolute value of alpha minus FL of alpha is less than 1 times b to the power e minus t. So if you combine equation 1 and 2, right? So if you combine equation 1 and 2, because you know you want to get this alpha minus FL of alpha divided by absolute value of alpha. So this one is less than b to the power e minus t over this one is less than b to the power e minus 1. So if you combine this, you get b to the power 1 minus. So that is what we wanted to prove there. Right? Okay, so the first part is completed. If you have a chopping, then you get the relative error is bounded by b to the power 1 minus t. Now the rounding case, right? Part 2. If this one is obtained by rounding, then you will end up with two cases. Because in rounding, right, the digit you are dropping, the first digit you are dropping is important in rounding. Right, if the value you are dropping is greater than or equal to 5, then you add 1 with the previous term. And if it is less than 1, then you don't add. Right, so that is what we learned in rounding. So in that case 1, right? So these are the two cases you will have when you are doing by rounding, right? Because if the first digit you are dropping, that is dt plus 1, is less than half of the base, right? So if it is base 10, if it is less than or equal to 5, less than 5, then you don't do anything, you just drop the terms, right? But if the first digit you are dropping is greater than half of the base, right? So that is in case if it is base 10, then if you drop anything more than 5 or equal to 5, then you add 1 with the previous term. And so that is what we do here. So you will end up with two cases, and in both cases you may have to look into the relative error bound. Right, so I am going to do everything in that way. right? So you all know that. Sorry. Right. So according to what we learned already, right? So we already know how to write FL alpha minus FL of alpha. So you do it again here, right? So in this case, you know FL of alpha is this. So when you subtract, you have this, right? So you don't have to worry about any other things, right? So this is 0 point dt plus 1 up to dn. But you all know dt plus 1 is less than b over 2, right? Half of b. So clearly, so this fraction is clearly less than 1/2 in that base, right? So because dt plus 1, the first digit is less than half. If you think about base 10, right? So if you think this as a base 10 problem, then you know it is less than half in that base, right? Times b to the power et, right? But we already have absolute value of alpha is greater than b to the power e minus 1, or greater or equal to e minus 1, right? So if you combine these two, you will get alpha minus FL of alpha divided by absolute value of alpha is less or equal to half b to the power e minus t divided by b to the power e minus 1. So that is half b to the power 1 minus t. Okay. So that is the error bound in case 1, right? So where you act like the same way you do in chopping, and because of the digit you are dropping, the first digit you are dropping is less than half of the base. Now the other case, right? So this one is simple. Now the other case. Now case 2. Right, so case 2 is this. Right, so this is, so in this case you can write FL of alpha in this way. Right, so you can write FL of alpha as, because with the last digit you add 1, right? So you can split it in two pieces and write it as this, right? So dt is point d1 up to dt plus 0.0001. So now if you take the absolute value of this, right? So what you have is this. Right, so if you subtract alpha minus FL of alpha, right, this is your FL of alpha. So from D1 up to Dn, you subtract 1 up to dt, then you will get t plus 1 up to n times b to the power minus t, and there is already an e, so b to the power e minus t. And then this number, if you change it to polynomial notation, you will get b to the power minus t, and then there is a b to the power e, so eventually you will get b to the power e minus t. So this in a way is 0 point dt plus 1 up to dn, right, minus 1. I can put the absolute value, or it doesn't matter, right? So, and okay, let me put an absolute value times b to the power e minus t. Next, so let's keep the absolute value so that you know that everything is plus. Right, so if you keep the absolute value, you get this 0.0 dt up to dn and this. Right, so now you notice that because this fraction is larger than half of the base, and so this fraction, if you think of base 10, this part is greater than 0.5 minus 1. So something bigger than 0.5 minus 1 is basically less or equal to, you can say it is less or equal to 0.5 or smaller, right? Because minus 1 plus 0.5 or 0.52 or 0.6 or 0.8 or whatever, right? So that number is obviously less than half. So then clearly what you have is this. Right, so because this fraction is less than half, so you get alpha minus FL of alpha is less than half b to the power e minus t. Right, but you already know alpha is greater than or equal to, or greater than or equal to b to the power e minus 1. Right, so if you combine both of them, you get alpha minus FL of alpha divided by absolute value as less or equal to half b to the power e minus t divided by b to the power e minus 1, that is half b to the power 1 minus 1. Right, so in any case, you see that in both cases, you see that the relative error is bounded above by half b to the power 1 minus t. So these terms are called error bound. Right, so these terms are called error bound in computation. So now let us see an example of how to determine the errors and error bounds in the computation. Right, so in a floating point system. Right, so Okay. Right, so let us see this example. Right, so two numbers are given, 1.75 and 1.25. Right. Say they want you to convert these numbers in floating point system, right? FL of 3, 2, first with chopping and then with rounding, right? And then they ask you to find the absolute error. I'll just give you a hint of how to do this because there are a lot of computations. So I will ask you to finish it, right? So first thing you need to do is to, so first I will write the steps. Okay. First I will write the steps. Step 1. Right, so you convert 0.175 into base 2, right? And step 2, right, you find FL of 1.75 in FL of 2, 3 with chopping. I will say bar, okay, with chopping. Step 3, you do that FL of 1.75 in FL of 2, 3 with rounding. Right. Next, you do the same thing for 1.25 as well, right? So right, so next you do everything for 1.25, right? And then you get FL of 1.25 bar and FL of 1.25, right? So you do this, and so after that, let me say step 4. So this is step 4, I say 4, 5 and 6, right? So these are step 4, 5 and 6 are here. So step 7, right? So you add FL of 1.75 bar plus FL of 1.25 bar, right? That is in chopping. And then next step, right? You do the for rounding. Right? So let me name this as Y1. Let me name this as Y2. Right? So after finishing step 1 up to step 8, right? Then what you do is step 9. right? So you convert y1 and y2 to base 10, right? So then you can find the error, right? So then the errors are here, right? So step 10. Error in 1 is absolute value. You add these two, so 3, right? 3 minus y1, and error in 2 is 3 minus 2. And so you have to finish all these steps for this problem. And so first you have to convert the number 1.75 into base 2, right? And then you do that for floating point, you do that for fixed point, and you do that for everything. Right? So I'm going to show you how we do this, right? In one example, 1.75 I will do, and then the rest you can see. Right, so the rest you can see. So let me start with 1.75. Right, so 1.75 you have two parts. Right, so step 1, 1.75, sorry, 75, right? So here you have integer part 1, fraction part 0.75. Both you have to convert to base 2, right? So you know one is 1, right, in base 2, right? So you can say 0, 1. 0, 1 in base 2. And so 1 is 1 in base 2 as well, right? So no worries, right? 1 is 1 in base 2 as well, right? So you know that. 0.75 you have to convert it into base 2, right? So the idea is this. You go back to Horner's algorithm. The first step we studied, right? So what you do? You multiply this by 2, right? From here to here, you multiply this by 2 and put the fraction part and put the integer part down and fraction part there, right? And then again multiply by 2, put the fraction part here, integer part here, right? So 0.75 is 0.11 in base 2, right? So 0.75 is 0.11 in base 2, right? So you have a number here, right? So then what you do? Then you write the complete transformation. Okay, so 1.75 is 0.11, right? So then what you do? You convert this number in FL of 2, 3, right? So that you know the formula, right? So if you want to get FL of 1.75 bar, right? So this is already this, so I believe there will be no change in this example, Right, so let me change the numbers a bit. So it's okay. First, for this example, you will keep it like this. Then in the tutorial, we will put a different program. Right. So here, FL bar, you have a formula, right? So we studied that formula, FL bar. Right. So chopping. Right. So you know this. Right, so b to the power e minus t times integer part of alpha times b to the power t minus e. Right. So here you know that alpha is 1.11, b is 2, e is 1, t is 3. So if you put all these values, you can find FL of 1.75 bar. Right. Similarly, you do that for FL, right? The other formula you have, and so you can do that for FL. Right? And then once you do that, you will do everything for 1.25, right? So then you find the rest, and you can follow in the same pattern, right? So the pattern which I show you, right? So now you have all the documents in your lecture notes, right? So you can follow all the steps and try to complete the problem. Right? So now this, for this problem, because I put this problem because you will have no change, right? So even if you go for floating point representation, you will still get 1.11. So there is no loss in significance, right? Similarly, for 1.25 also you will have the same thing. You will not lose anything. So eventually your error will become 0. Right? So that is why I gave these simple numbers, because first you try to practice the pattern, right? How to do this problem. Right? So now let me give you another example. So this will give you a little bit more challenge, but you always follow the same pattern. Right, so in this second example, if you try the same pattern which I explained you for the first example, you can see the differences, right? So you will actually see the error. Here also, and so let us compute the absolute error as well in this problem. Okay, so so this example again, example 2 also, you follow the same steps, right? So you convert the numbers into base 2, and then you convert the numbers into floating point with chopping. You convert the numbers into floating point with rounding, and then you add the numbers in floating point, the representation, and then you convert it back to base 10, and then you compute the error, right? So that is the way to answer these type of questions. So I'm going to stop here with this. They already posted a tutorial there, right? So that is for chapter 1. You can work on those tutorial, and when the appropriate time comes, we will do the tutorial as well, right? So this is the end of chapter 1. In the next class, we are going to start chapter 2, right? So we will stop chapter 1. Today's class with this last part of the chapter 1. We will start chapter 2 in the next class.